Alrighty, today is our last regular class meeting, and we're going to cover the concept of power factor correction today, which builds off of the complex power relationships that we went over last Thursday. But before we get started, I just want to let you guys know my internet connection here at my office has been kind of spotty today. I was trying to help a student out for the last 30 minutes or so, and I think I got dropped 2 or 3 times. So, apologize if the lecture just shuts down abruptly because the internet kicked me off. I'll get right back on and we'll go from there. All right, so let's see. This first problem we have says that when connected to a 120 volt RMS 60 hertz power line, a certain load absorbs 4 kilowatts of power at a power factor of 0.8 lagging. And we're asked to determine the value of the capacitor that should be placed in parallel with the load to raise the power factor to 0.95 lagging. So what we have is a simple system. 120 volts RMS here. We don't know what the angle is, and it's not particularly important. At 60 hertz. And then we have our load. And we're told that the load is 4 kilowatts at 0.8 lagging. So what we are going to need to do is find, and then the last thing here is what we're going to do is we're going to figure out what's going on when we put a compensation capacitor C in parallel with our source. And that compensation capacitor, its role is to increase the power factor to 0.95 lagging. All right, so our first step is to figure out what the complex power absorbed by our load is before power factor correction. So can anybody tell me how to do that?
Is it the power divided by the power factor?
So because we have kilowatts here, that is average power. So that means our apparent power is going to be P divided by the power factor, which is exactly what you said. What are we going to do for our angle?
The inverse cosine of the power factor.
All right. And because our power factor is lagging, should I have a plus sign here or a minus sign?
A plus sign?
That is correct. Positive. Our angle should be positive. So if we throw in our numbers, this is 4 kilowatts divided by 0.8, angle inverse cosine of 0.8. And this is going to give us angle 36.87 degrees kVA, or in rectangular form, 4 plus J3 kVA. Now, after power factor correction, and so I guess really I should hear PF old. We're going to do the same thing. So one of the keys about power factor correction is that the real part of the complex power does not change. So when we put that capacitor in, it's going to change the reactive power that's being absorbed by the load, but it's going to have no influence whatsoever on the average power. So we're just going to have P divided by PF new with an angle of inverse cosine PF new. And because we want our power factor to be still lagging, we're also going to have the positive sign there. So this is 4 kilowatts divided by 0.95 with an angle of inverse cosine 0.95. And that gives us 4.210. You can't really see the period there. With an angle of 18.195 degrees kVA, or in rectangular form, 4 plus J 1.315 kilovolt amperes. So we know what our old complex power was before power factor correction. We know what our new complex power is after we've applied our capacitor. Now we just need to figure out what the capacitor value is that makes this happen. Well, complex power absorbed by our capacitor is going to be negative J omega C times VRMS squared, where VRMS is the magnitude of the voltage drop over the capacitor. And this is also going to be equal to S new minus S old. So S new minus S old is minus J 1.685 kVA. And so we can rearrange and find that C will be equal to positive 1.685 kVA, because we have a negative sign here and a negative sign there, so they're going to cancel each other out, divided by omega. Who can tell me what omega is going to be in this problem? Anybody have any guesses?
It'll be the 60 hertz multiplied by 2 pi.
Absolutely right. So 120 pi. And what is the magnitude of the RMS voltage drop over the capacitor?
120.
120 volts RMS squared. And so $310.389 microfarads. So a little bit off right here, probably due to a rounding error. Good enough for government work. So this is the basic process for power factor correction. It's really just a few simple steps. You need to know the old complex power. You need to know the new complex power. Take the difference, all for C. That's really it. So any questions regarding this problem before we move on to number 2?
I'm good.
So number 2, apparently we're in Europe because we have a 230 volt source at 50 hertz, is used to power a single phase induction motor with an impedance of 25 plus J 10 ohms. We want to know the value of the capacitor that should be placed in parallel with the motor to raise the power factor to 1. So how are we going to, so let me draw a little picture here, I guess. And again, we're gonna try to put a capacitor in and figure out what that value is. So my first question to you guys is, how are we going to find S old in this problem?
S old is the complex power of the motor, right?
That is correct.
I'd use the alternative relationship using VRMS and the motor's impedance.
Okay, so what I believe you're referring to is, we know that the complex power is going to be the voltage drop times the complex conjugate of the current, where the complex conjugate of the current is the voltage drop divided by the impedance of the motor conjugate. And so what this gives us is the magnitude of the voltage squared divided by the conjugate of the motor's impedance, if I've done my math correctly, which I believe I have. So that would be 230 volts RMS squared divided by 25 minus J10 ohms let's do it here. 1.964 angle 21.801 degrees. Let's see, kilovolt amperes, which is 1.824 plus J 0.72730 kVA, if I've done my math correctly. Anybody get something similar?
That's what I got too.
All right, so we can actually skip ahead here, and let me explain my reasoning. We know that the average power that's absorbed by the motor is going to stay the same. And we're changing the power factor from whatever it happens to be right now, didn't bother calculating it, to a power factor of 1.0. Well, what does a power factor of 1.0 mean? Anybody have any idea?
The inverse cosine of 1 is 0. I'm
So
not
that
sure what
angle,
practically that means.
yeah, so that means that the angle of the complex power is 0. So if I have a complex number, 10 angle 0 degrees, is that complex number purely real, purely imaginary, or neither?
Purely real.
Purely real, right? So whenever I want my load to operate at a power factor of 1, that means that I'm just getting rid of all of the reactive power. So the reactive power that my capacitor needs to supply is that 0.730 kVA. I don't need to be, I'm going to wind up having 1.824 minus this, which is just going to be that negative J 0.730 kVA. So I don't actually need to figure out S new in this case, but it's specifically because I know that my power factor new is 1. Does that make sense at all?
Yes, sir.
So from this, C is 0.730 kVA divided by 100 pi, because our frequency was 50. So 50 times 2 pi is 100 pi, times 230 volts RMS quantity squared. I get 43.901 microfarad. Again, really, really close, but with a little bit of rounding error. So these two were pretty, in my mind, were pretty easy. The last problem I'd like to look at is actually homework 24, problem 4. So it's the last homework problem of the last homework set that I expect you guys to be able to do. And we're going to take a look at this guy because it's actually significantly more difficult than these problems and much more difficult than anything that I would put on the exam, but could be useful to you guys to kind of really tie things together. So let's see. All right, so we'll use my numbers for this. So we have a circuit, fairly straightforward. R is 4.5 ohms. And here we have a load. We are told that the load draws 12.4 kVA at a power factor 0.58 lagging. So I'll try to scram into there. We're also told that the magnitude of this current, I load, is...
Did you say this is a web work problem?
Yes.
Okay.
Homework 24, problem 4.
Okay.
Yes.
Thank you.
Let's see, 25 amps RMS. And we're told that PF new is supposed to be 0.93 lagging. And that our frequency is 60 hertz. So our goal here is to figure out what the value of the capacitor C is that makes this happen. But we're going to have to do several additional steps along the way in order to figure out some things. So for instance, we are not given the value of the voltage Vs, which means if we try to apply our equation, C is equal to negative Q cap over omega VRMS squared, we don't know what VRMS is. So we're going to have to figure that out along the way. Additionally, instead of being just simply our voltage source being simply connected to our load, we also have what I would characterize as a transmission line impedance that we're going to have to worry about as well, because that's going to cause some losses, which is going to change the power factor that the source is operating at too. So we're going to approach this in a pretty similar way, but there's going to be a little bit more legwork that we have to do to start things off. So let's look at what we can figure out. Do we have enough information to figure out what the complex power absorbed by the load is?
Yes.
All right. So how would we go about doing that?
It would be the power divided by the power factor.
So the units for the power is volt amperes, Is that reactive power, average power, or apparent power?
That is apparent.
So apparent power is the magnitude of the complex power by definition. So because we have units of volt amperes here, we do not need to divide by the power factor. Right? We've been told what the magnitude of the complex power is. So it's
Yes.
critically important that we pay attention to these units. So we're going to have 12.4 kVA. That doesn't look like kVA at all. And our angle is going to be the inverse cosine of our power factor, old, which is 0.58. And so that is going to give us, let's see, 12.4. Angle inverse cosine 0.58. That gives us 12.4 angle 54.549 degrees kVA. And in rectangular, $7.192 plus J 10.101 kVA. So we know the complex power absorbed by our load. Do we have enough information to determine the complex power absorbed by our 4.5 ohm resistor?
Yes.
Yes.
Could we just do I squared times the resistor?
So absolutely. The reason why we can simply do I squared times R here is because we know that the impedance of the resistor is purely real. So we can treat this like anything else, right? So I squared times R is going to give us our complex power, and it's going to be a purely real value. If we went through the derivation, just I'll do it down here and then erase it. So we know that S is equal to V times I conjugate is equal to, sorry, that's the wrong one. I Z times I conjugate is magnitude of I squared times Z. Well, that's exactly the same thing as I squared times R in this case. So that is 25 amps RMS squared times 4.5 ohms is 2.812 angle 0 degrees kilovolt amperes, or 2.812 plus J0 kVA in rectangular form. So from these two pieces of information, we can now determine how much complex power our source is supplying before power factor correction. Does anybody have any problems with that statement?
No, sir.
What I'm saying is that the complex power supplied by the source is the exact same as the complex power absorbed by our resistor plus the complex power absorbed by our load. And this is true before power factor correction. So when I add these two together, let me just make sure, yeah, I get 14.217 angle 45.276 degrees kilovolt amperes, which is 10.004 plus J 10.101 kVA. Alrighty, so now that I know my complex power absorbed by my source, this is effectively S old, okay? Because that's the complex power supplied before power factor correction. Now we can find S new, and it's going to be our average power, 10.004 kilowatts, divided by our new power factor, 0.93, with an angle of inverse cosine of 0.93. Which I get to be 10.757 angle 21.565 kVA, or in rectangular form, 10.004 plus J 3.954 kVA. So we know S old, and we know S new. So what pieces of information are we missing to be able to solve for C?
We could find our frequency, but we're missing our voltage, VRMS.
Okay, so let's talk about how we're going to find VRMS. So I'm going to draw something right here. And actually, quickly, because it's an RMS value. So we know the complex power absorbed by our 4.5 ohm resistor and our load together, correct?
Yeah, correct.
So we could find that voltage VRMS. So what I'm saying, we know the power absorbed by this guy and the power absorbed by this guy. So we could say that S, the total power there, is equal to that VRMS value times I load conjugate. But we don't know I load conjugate, right? I could, however, alter my equation ever so slightly and say that the apparent power is the magnitude of VRMS, which is what we're trying to find out, multiplied by the magnitude of I load, which we do know. So do we know the apparent power absorbed by those, the resistor and the load together? All right, so let me phrase this slightly differently. We agree, or at least I believe we agree, that we know what the complex power absorbed by the 4.5 ohm resistor and the load is together.
Yes.
Okay, and we found that right here. What I just talked about was this value, which is identical to this value right here. What I'm asking you is, do we know the apparent power absorbed by that resistor and the load together?
Yes.
Right. Why?
Because there's an imaginary number, right?
So the apparent power, by definition, is simply the magnitude of the complex power. So since we have our complex power expressed in polar form and rectangular form, if we want the apparent power, we just look at the magnitude right here. So it's 14.217 kVA. If we wanted the real power, it'd be this guy. If we wanted the reactive power, it would be this guy. So if we know the complex power, we, by definition, know average power, reactive power, and apparent power. All right, so if S is equal to VRMS times I load magnitude, then that means that the magnitude of the RMS voltage, which is really the only thing we need, is our apparent power divided by the magnitude of I load. So that is 14.217 kilovolt ampere divided by 25 amps RMS. So 14.217 times 10 to the 3 divided by 25 gives us a voltage of 568.68 volts RMS. So this is the voltage drop over the capacitor, or the magnitude of the voltage drop over the capacitor. So what else are we missing? So we can figure out omega. It's going to be 120 pi. We know what VRMS is. Q cap is just the reactive power absorbed by the capacitor. So that is effectively just S new minus S old divided by J. So S cap is S new minus S old which is going to be negative J 6.147 kVA. So from this, C is 6.147 kilovars, or that should be a 6, there we go, divided by 120 pi times 568.68 volts RMS squared. 50.419 microfarads. Just one here. All right, so that problem was a bit more involved, but I intended for it to help us kind of review our different complex power relationships, since we needed to kind of pick and choose the different pieces that we would use in order to work towards our final answer. I would say, though, that on the exam, you should expect your complex power problems to be more in line with the in-class assignment problems, or the ones on old tests, which to me are maybe one tiny increase in difficulty. So I might make you do a little bit extra work. But anyway. All right, so any questions on power factor correction or anything? Nobody
I'm
said?
good.
Okay. So tomorrow morning at 10 a.m., we will have our review session for, roughly 2 hours. I do have some time this afternoon if anybody wants to ask any questions for the upcoming exam. Then, we have the review session tomorrow. I have some office hours tomorrow afternoon as well that I can answer questions. And then Wednesday, I'm in Bossier, and Thursday I will probably be working on getting all of my grading finished before grades are due at the beginning of next week. So Thursday probably not going to be available for questions. So that means if you got any questions about any of this stuff, you need to ask them either this afternoon or at some point tomorrow, or forever hold your peace.
Yes, sir. Loud and clear.
Cool deal. All right, let's see. Somebody I think is doing something in the chat. Let's see if I can see who that is.
I have a quick question. How is the grading going to be laid out? I understand that we didn't have any mini labs, I think, this quarter.
So because we didn't do any of the mini labs, you did exactly 100% of all the mini labs that were assigned. So you will get 100% credit.
Okay, so basically the grading layout's just the same. We're just getting free grades from the mini labs, right?
Got to do stuff, yeah.
Okay, just making sure.
I don't think anybody will be disappointed by that result. Hope not anyway. So yeah, you will all be receiving, oh goodness, what did I just do? Full credit for the mini lab assignments.
Okay.
With regards to the in-class assignments, I think I mentioned it in class previously, but I'm not sure, so I'll state it again. If you, for whatever reason, didn't turn in any in-class assignments, you can absolutely still turn them in for full credit, and I will be dropping 3. So that means if you didn't turn in 3, you have 100%. If you turn in, I'm not offering any bonus credit for you turning in more than what you need. So the maximum score that you could get on your in-class assignments is a 100%. And if you turned it in, you get 100%. And if you didn't turn it in, you get 0. That's the grading scale for that. So you either did it or you didn't.
How much are the assignments worth again? I forgot.
Let's see if I can find the syllabus real quick.
Were they like a part of your attendance grade or something?
I don't know. It's been.
They're worth 5%.
It's 5%.
Thank you.
Okay, I thought I remember that.
So let's see. All right. So the homework, it says, is worth 15%, 10% for assignments, and 5% for a notebook, but we're not doing a notebook. I think I mentioned that on the first day of class. So that was just left over for me copying and pasting the previous thing. So your web work is 15% of your final grade. Those are turned off effectively the day of the quarter at 5 p.m. So you have until Thursday, the 20th at 5 p.m. to complete your web work assignments. So that's a week and a couple of days. No, that's not right. The 13th. So you have until this Thursday at 5 p.m. Honestly, your grades aren't due until Monday, I think. So I could extend it to be over the weekend, and it wouldn't. I wouldn't have a problem with that. I just don't want anybody complaining that I'm supposedly making you do stuff after the quarter is over. That is not remotely the case. I am allowing you to increase your grade after the quarter is over, and you should be thankful I am so benevolent. And also,
Could you do that? That'd be really cool.
yeah, I can do that. I got no problem doing that. So I'll go through and take care of that probably this afternoon.
Thank you.
To be clear, I'm giving you guys a few extra days to work on your web works to bring your scores up. I would glean through them today, this evening, if at all possible, just to see if there's any questions that really stand out that you're not sure how to do. Just because my availability, again, after tomorrow afternoon is going to be pretty sparse to answer questions and things like that. I may have some availability this weekend after I finish making out you guys final and all that kind of good stuff, and then taking care of some stuff for circuits too. But effectively the 12th, the 13th, and the 14th, I will be out of pocket finishing things up. All right, so homeworks, I'm giving you guys a little bit extra time to do them. The in-class assignments, again, are worth 5% of your grade. There were 23 of them assigned, I believe. So if you turned in 20 of them, you get 100%. If you turned in less than 20 of them, you get less than 100%. If you turned in more than 20, you also still just get 100%. The mini labs were 5% of your grade. So everybody's just going to get the full 5% for that. And then as far as your exams go, they're each worth 30% apiece, but whichever one you score the lowest on only counts for 15%. So yeah, hopefully this exam 3 won't be any of you guys' lowest grades, but should be pretty easy to figure out what grade you need to make on this particular exam based on your homeworks and all that kind of stuff, and all the other information that you have. So any questions about how any of the things are graded?
I am so sorry. Can you repeat the test grading part again? I'm
Sure.
so sorry.
Oh, it's no problem. Whatever test you score the lowest on counts for 15% instead of 30%.
Okay.
So whatever test you score the lowest on only counts for half of what the other tests do.
And so like the other 2 tests are still worth 30, right?
That is correct. Yeah.
Okay. All right. I'm
Yeah.
good.
To do poorly on one test without it totally wrecking your chances for making an A in the class. I believe as long as you can make above a 33, then on all of your tests, as long as, like a 30, you'd have to score under a 33 to automatically not be able to make an A in this class based on these weights, I believe. So trying to be reasonably lenient.
I appreciate it.
Any other questions? Oh, I got something else in chat. Let's see what's up there. In class. I don't know how long ago you asked me to say that stuff, Rhett, but in class assignments, again, if you turn them in, you get full credit. If you didn't turn it in, you get 0 credit. There were 23 of them that were assigned. I will only be scoring 20 of them. So you cannot get a greater than 100% on your in-class assignments. So yeah, so I'm going to be grading them out of 20. So if you did 17 out of the 20, that means that you would get an 85. If you did 20 out of the 20, you would get 100. If you did 23 out of the 20, you would still get 100. You can turn them in until let's make it Monday like the homework. So if you missed any, watch the old videos, figure them out, and then turn it into the submission portals. I don't have any of them set to reject late assignments, or at least I don't to my knowledge. So if you have one that you didn't do and you're worried about getting some extra points, go ahead and solve it and then send the submission in, and I'll still count it without any penalty. All right, any other questions regarding the syllabus 10 weeks into class, or any of the homework assignments or in-class assignments, or just anything circuits related?
I was curious
No,
if the
sir.
final was still going to be non-cumulative.
That is
Or if it
correct.
was-
It is non-cumulative, meaning it is
Okay.
material from lecture, let's see, 16, which is op amps, all the way through today's lecture, which is power factor correction.
Alrighty.
Any other questions?
Could you go over op amps? Just a quick like example, like just explaining like how they the voltage drops like over the VO.
Sure. Let me give myself a new sheet of paper here. Edit, document, and all right. Give me just a moment, and I'm just going to pull an op amp problem from one of the tests I posted for you guys. I just got to find one. Let's see. All right, this one looks ugly. So the one I'm looking at is number 27 and 28 on the fall 2019 exam. All right, so give me just a minute to draw this bad boy out. Come on, pen, do your job. There we go. So this one looks pretty gnarly. Dang it. Hold on. But in all honesty, it's not that particularly difficult to solve. Let's see. All right, so this is a real ugly looking op-amp circuit, and you're asked to find two voltages. In problem 27, you're asked to find the voltage present at the non-inverting terminal of the op-amp. So that means that we are looking for this voltage at this node, which I have labeled as V+. And we're going to be employing our two ideal op-amp rules. So just for reminder's sake, those two rules are: number one, there is no voltage difference between the input terminals, which means that the voltage I have labeled as V+ is the same as the voltage V-, which is right here. And rule number two, no current may flow into or out of the input terminals. So that means that this current is 0 amps and this current is 0 amps. So let's figure out how we can find that voltage V+, and then use that to answer the next question, which is the voltage V out. So does anybody have any ideas how we might go about solving for the voltage V+?
ACL. So if we do KCL, we know that there is 1.2 milliamps flowing up into this node, which means that we know that there is 1.2 milliamps flowing to the left through the 4.1 kilo ohm resistor. How does that help us find the voltage V+? It doesn't.
So it's not necessarily that it doesn't. I would argue, though, that instead applying KVL would be of better use. But we're still actually going to use that exact same piece of information that we got. So all of these grounds are one single node. So if I start here and follow that current around this path, doing Kirchhoff's voltage law, what I will find, oh, and another thing I guess that I should be clear about, so I'll redraw that in just a second. This voltage V+ is a nodal voltage, which means it is the exact same thing as the voltage drop over that current source. So with that in mind, if I start here and go around this loop, applying Kirchhoff's voltage law, I have negative V+ plus 4.1 kilo ohms times 1.2 milliamps plus 6.1 volts is equal to 0, which means V+ is equal to 4.1 kilo ohms times 1.2 milliamps plus 6.1 volts. So 4.1 times 1.2 plus 6.1 is 11.020 volts. So does everybody understand the circuit analysis that I just did there? Or does anybody have questions or anything about it? So using KCL wasn't entirely fruitless. It's just by applying op amp rule number 2, we could have came to that same observation that 1.2 milliamps of current must be flowing to the left through the 4.1 kilo ohm resistor. So the KVL loop is really what helped us find that voltage. Now, for the next part of the problem, what we are going to do is we are going to apply KCL. We're going to apply it at this node. And so what I mean by that specifically is we're going to take this current, and this current, and add them all up and set it equal to 0. But before we do that, I guess there's one other thing that we could do. The 3.7 kilo ohm resistor and the 9.2 kilo ohm resistor, how are they connected?
Series.
So I could combine them into a single equivalent resistance, which will actually potentially make my math a little more straightforward, right? So 9.2 plus 3.7, I believe is 12.9. Now it looks like a single resistor there, and that's going to allow me to get an equation for my output voltage in a little bit easier fashion. So I'm going to have V minus voltage present at my inverting input terminal, which is exactly equal to the V plus we just solved for, minus 0 divided by 5.3 kilo ohms, plus V minus negative, so positive 3.9 volts. Did I draw my polarities there? Oh, so, shit. All right, never mind. So in the actual problem on the exam that I was talking about, the polarity of that 3.9 volt source was switched. Positive polarity was on the left, negative polarity was on the right, but we'll work it out as it's drawn here. So that will be minus 3.9 volts divided by 4.7 kilo ohms. And then lastly, the current directed to the right is going to be V minus V out divided by 12.9 kilo ohms. And so we can rearrange this and say that 12.9 kilo ohms times 11.020 volts over 5.3 kilo ohms plus 11.020 volts minus 3.9 volts divided by 4.7 kilo ohms plus 11.020 volts divided by 12.9 kilo ohms is equal to V out. And then we would just put that into our calculator. So for any op-amp problem that you're unsure of how to work, there's really only a couple of steps to it. The first thing is you figure out this voltage V plus by any means necessary. And the second thing you do is apply Kirchhoff's current law at the inverting input node. And that should be enough to give you V out for pretty much every op-amp problem I could possibly ask you.
Thank you.
Problem. And that problem right there is, my best guess would be that's the hardest op-amp problem I've ever asked on an exam. Any other questions about anything? Alrighty, well, we have the review session tomorrow at 10 a.m. So please go through, like I said, the WebWorks and all that kind of stuff. If you have any questions about that, happy to answer them. I think I put at least 3 more old tests up to give you a wider base to study for the exam 3 materials. And again, none of those questions that I added have solutions. So if you have any questions about how to solve any of those guys, I'd be happy to answer them. Yeah, let's just have a good productive study session tomorrow, or review session tomorrow. And then if anybody has any other questions that they think of during the course of the day, just hit me up on email and we'll hop on Zoom and figure things out. All right, you guys have a great rest of your afternoon, and I will see you all tomorrow morning.
You too. Thank you, Dr. Hartman.